You're watching Global Toronto. This is Global News at 5:30.
Good evening and welcome to Global News. I'm Vita Purhasham and here are today's breaking stories. What's happening? Great, the lights are out. Anyone know what we're going to do about this? We have to get back on air.
Alright, well, we have photovoltaic cells that we can use.
But they're so small, how are they going to power the whole station?
I don't know, I'm a producer, not an engineer. But I do know a scientist that can help. In the meantime, I will get our photovoltaic cells up and running.
Okay, that's a good idea. You can go in. Oh, got a text. Apparently the whole city's experiencing the blackout, not just us.
Don't worry, Professor Evergreen is on her way. In the meantime, we should take advantage of this situation and produce a new segment. We can call it When in Blackout.
Okay, great idea, just horrible name. Work on that.
Anyways, the lights should be back on in 3, 2...
Oh, I guess photovoltaic cells really do work. Guess the city should rely on those as opposed to Toronto Hydro.
Okay, everyone, let's take 5. We'll be back at 5:40. See you then.
Okay, sounds good.
You're watching Global Toronto. This is Global News at 5:30.
Good evening and welcome to Global News. I'm Vita Purhasham and today we have a special guest. Here to explain the science behind photovoltaic cells, Professor Evergreen. Welcome, Professor.
Thank you for having me.
So, can you give us a little background on these devices?
Well, photovoltaic cells, also known as PV cells, are specialized semiconductor diodes that convert visible light into direct current. Now what this means is that PV cells are made up of electrodes, an anode and a cathode, which are connected to semiconducting layers. There's a positive and negative layer, most commonly made out of silicon, and in between them is the positive-negative junction, or the PN junction. P for positive, N for negative.
And when radiation hits the PN junction, a voltage difference is produced that lets electrodes draw a current flow from the device?
How do you know that? But that's right, totally. And that's essentially the basis of the photoelectric effect. But that's just kind of the basic outline of how PV cells work. While the science behind it is good to know and to understand, it's also important to know how science and technology kind of got to this point to create a device like this, which we'll get to in a bit.
So you said I hit the basis of the photoelectric effect. Would you mind going a little more in depth about it?
Okay, the concept of the photoelectric effect is actually quite simple. It just explains that when light hits the surface of a solid, under certain circumstances, the energy transferred by the light wave is enough to push the electrons of the material around and even to free them. Materials that exhibit this behavior are deemed photoemissive materials, and the ejected electrons are called photoelectrons, although they're pretty much the same as any other electron.
And it's with this effect that PV cells work?
Exactly. Remember how I mentioned that there was a negative and positive semiconductor layer? Well, the PN junction only allows electrons to move from the negative layer to the positive layer, not the other way around. So when the light hits the device and enough photons are absorbed by the negative layer, electrons are freed from the negative layer, passing through the PN junction to the positive layer. When there's an external load connecting the two layers, a current is created.
That's really cool, but earlier you said the energy from light waves were the cause of the electrons being freed. Now you say it's photons. Which is it?
Actually, the energy from light waves and photons are essentially the same thing. And fun fact, it was Einstein who proposed that light is composed of these tiny particles called photons. This was then deemed Einstein's quantum theory of light. However, photons are not exactly particles as they have no mass. They're actually quanta or packets of light energy.
So is there anything that supports what Einstein theorized? An equation maybe?
There is. According to him, each photon carries a packet of maximum kinetic energy. The way to calculate it is by using the equation. Energy of the photon equals h times f, where e is the quantum of maximum kinetic energy, f is the frequency of the light, and h is Planck's constant, which has a value of 6.63 times 10 to the power of negative 34 joules times second. But there's more to it. You see, when there is a collision between a photon and an electron, the energy carried by the photon, hf, is absorbed by the electron. However, when the energy is less than the work function, the electron doesn't escape from the solid.
Can you explain what the work function is?
The work function, W, is Planck's constant multiplied by the threshold frequency in the photoelectric effect. A photon with a threshold frequency can barely provide enough energy to eject an electron from a solid. However, it still does. It's just that the electron will have no kinetic energy. So a photon with a higher frequency than the threshold frequency will have its extra energy go into the kinetic energy of the electron.
I bet there's an equation associated with this, right?
Of course, the work function itself is calculated with the equation W equals hf naught, and the kinetic energy of an electron is calculated using Ek equals hf minus hf naught. However, we know that hf naught is equal to W, so we can simplify Ek equals hf minus hf naught to Ek equals hf minus W, or the work function.
Well, what if you kept the frequency the same and you increased the intensity of the light? Would that make an electron escape?
When you increase the intensity of light, you increase the number of photons that arrive to a specific point per second. For monochromatic light, regardless of the intensity, if the energy is less than the work function, the electron won't escape. It's like if you fired a bunch of low-energy ping-pong balls at an elephant. You can fire thousands and thousands, but the elephant won't fall over. But if you fire a really high-energy cannonball at the elephant, it will fall over.
It's amazing to think that Einstein theorized all of this, obviously with the help of previous scientists' work. I guess you could say that his theories really helped regarding the photoelectric effect.
He definitely enlightened our way of thinking.
Would you mind solving a quick problem for the viewers at home?
Not at all. I love science.
So here we came up with a simple question. Let's guide our audience through it. The question is, what is the maximum kinetic energy of a photon if the light has a wavelength of 475 nanometers?
This one's easy. Let's take it step by step. So first off, we need to convert 475 nanometers to meters. Using the factor label method, we see that 1 nanometer is equal to 1 times 10 to the negative 9 meters. Therefore, 475 nanometers is equal to 4.75 times 10 to the negative 7 meters. We also know that the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. We also know that air has an index of refraction of 1.0003. Using the equation N equals C over V and rearranging to solve for V, we see that V equals 3.0 times 10 to the 8 meters per second, all divided by 1.0003. This gives us 2.9991 times 10 to the 8 meters per second. To find the frequency of this light, we use the equation V equals lambda times frequency and rearrange for F, frequency. We then get that F equals 2.991 times 10 to the 8 meters per second, all divided by 4.75 times 10 to the negative 7 meters. This equals 6.3 times 10 to the 14 hertz. Now that we have the frequency, we know that Planck's constant is 6.63 times 10 to the negative 34 joules times second. We can plug it into the equation E of the photon equals hf. And we see that energy of the photon equals 6.63 times 10 to the negative 34 joules times second, all multiplied by 6.3 times 10 to the 14 hertz. This equals 4.2 times 10 to the negative 19 joules. Therefore, the maximum kinetic energy of this photon is 4.2 times 10 to the negative 19 joules.
impressive. Thanks for coming on the show today to teach us about PV cells, the photoelectric effect, and Einstein's quantum theory of light.
It was really no problem. I love teaching people about science because I love science!
Thanks for tuning in to our new segment, Out of the Dark. Tune back in next week where we analyze Newton's 3 laws of motion. Have a good night.